Thank you so much for the introduction. Very happy to give a talk on some of my PhD research looking at sort of phase segregation and mixed halide perovskites that I did back when I was at Notre Dame. As I mentioned, I'm currently at Caltech doing some different work, but still in sort of a related area. So with that, I'll just sort of jump into things. So I know obviously this is a very perovskite and solar kind of crowd, but I think just sort of, a little bit of background, I think it's useful to kind of link back to kind of structure property relations, especially for our material scientists or inorganic chemists that might be in the crowd. As most of us know, we have these lead halide perovskites with their ABX3 structure. But the important thing, of course, is that this structure directly dictates the optical properties and the actual energetic alignment in the system. And so if we think about in terms of sort of a molecular orbital picture, it ends up being that the conduction band, or if you're more on the molecular side, the LUMO level, is mostly created through these sort of lead, slightly anti-bonding or slightly non-bonding orbitals. And the interesting thing is the valence band position for these perovskites, or equivalently sort of the HOMO level, this is mainly produced by mixing of these lead and these halide orbitals in mostly sort of an anti-bonding type orbital. And so what that means is that this band gap, the energy required to actually excite the electrons, of course, this is directly dictated by the halide ions in the system. So when it comes to the ABX3 structure and the optical properties, these halide ions become sort of the key driver for tuning a lot of these properties. Right? And if you think about something like using lead iodide versus pure bromide versus pure chloride, you get this very large tunability in the band gap and thus the optical properties, absorption and emission across a fairly wide range. And this is something that I think it's easy to kind of forget about the fact that this is really sort of unique for most semiconductor systems. Most systems don't have this large degree of tunability. And of course, this tunability and the absorption properties, this has been something that people have been very interested in when it comes to applications like tandem solar cells, right, where you have silicon as one low energy photon absorber and a much more wide bandgap perovskite as the higher energy absorber. And you get this huge tunability across the visible spectrum. But as most of us are aware at this point, these perovskites, especially the mixed halide perovskites that give you this absorption tunability, they have this really fundamental drawback, and that's the fact that this nice homogeneous mixed halide perovskite phase, as soon as you give it a little bit of light energy and overcome this barrier of about 30 kilojoules per mole, which is something that we have sort of measured in the past to look at the thermodynamics of the system, you end up creating basically these phase segregated regions where you have an iodide-rich and a bromide-rich domain that are right next to each other. And the reason why this is an issue is these iodide-rich regions basically act as charge recombination centers. So going back to kind of the band diagram picture, you have a wider band gap bromide-rich domain right next to a lower band gap iodide-rich domain. All of your charge carriers are going to want to just go directly downhill, and you're going to start getting a lot of recombination. And essentially, those important charge carriers that you spend all this time producing, they end up getting lost to just radiative and non-radiative recombination pathways, and this essentially kills your efficiency. So on the one hand, we have this lovely tunability of absorption properties, but if you start shining light on it for too long, you get this movement of these halide ions. And this has sort of been something that people have been studying for a while and attempting to sort of mitigate or solve this process, because once you can get around this issue, then you can unlock a lot more interesting properties and interesting applications for these materials. Okay, so 3 minutes of a little background on that. When it comes to sort of the mechanism, though, of how this phase segregation, specifically halide ion segregation, occurs, over the years, there's been a few sort of mechanistic insights that have sort of come in. There's some folks that induce sort of this idea of Polaron-induced strain. And so that's when sort of the charge carriers are coupling to the lattice vibrations, and that can induce all sorts of interesting physical interactions that have been purported to sort of drive this phase segregation process. There's other folks at Notre Dame who've looked at more of the thermodynamics or the free energies of mixing that change under illumination. But recently, in the last couple of years, there's been a lot of interest in sort of looking at the effect of charge carriers. And there's been some interesting results looking at sort of gradients in charge carriers and accumulation of different charge carriers and how that basically is impacting this phase segregation process. And so, as a little bit of background, sort of in recent years, there's this general insight that charge carriers, and specifically holes, seem to be playing kind of a unique role in the overall phase segregation process. And this has been something that was sort of, illuminated over the past couple of years. But when I was in my PhD starting to look at these materials, that was sort of the basis of the field. And we wanted to kind of push a little bit more and look at the mechanism using kind of very specific spectroscopic methods. So transitioning gears a little bit, just to kind of tell the story of this project and to be a little bit honest about sort of the serendipity that might have occurred in this project. Initially, what I was doing was looking at methylmonium lead, bromide iodide, 50-50 halide ratio for transient absorption experiments. So in this case, originally we were looking at electron injection from the halide perovskite into TiO2, right, our prototypical electron transport layer, using a transient absorption spectrometer, which uses this pulsed laser excitation to actually do the experiment. And just sort of, very much so visually, we're able to see that at the start of the transient absorption experiment, which I'll talk more about transient absorption and kind of give a little bit of background on that in a slide or two. But essentially what we see is from the pulse laser excitation, we're exciting our perovskite. This is just a very, kind of crappy cell phone photo that I took. But we noticed something just empirically, and that was that the photoluminescence that we're seeing from this laser excitation started as red. This little dot here, this is the white light probe used for transient absorption. And then after our 10 minutes or so that we take to collect our transient absorption spectra, we were sort of just visually saying, wait a minute, we're seeing what looks like kind of a green emission on the films. And it looks like this is, emission that kind of is roughly in the region where methylmonium lead bromide absorbs. And then if we look at the actual transient absorption spectra, and again, I'll explain what these spectra mean and what these features mean in a second, but essentially, initially at the start of the experiment, we saw basically one feature coming from where we expect sort of the mixed halide perovskite base to appear. And after 10 minutes of this laser radiation doing this transient absorption experiment, we started to see multiple different fingerprints in the transient absorption spectra that essentially looked very reminiscent to phase segregation. And we were a little bit surprised about this because, when we typically see phase segregation is under conditions of steady state excitation. So if you have some sort of, lamp or some sort of continuous wave laser, typically you need this continuous excitation on the perovskite in order to induce this phase segregation and start forming these iodide and bromide rich domains. So that's typical for phase segregation is sort of continuous wave, or just if you have a xenon lamp like a solar simulator, that's what we expect to induce phase segregation. When we're doing spectroscopic experiments like transient absorption, which uses pulse laser excitation, we have these near instantaneous laser pulses that are only 150 femtoseconds in pulse width. So for all intents and purposes, this is kind of like an instantaneous excitation. And also between the pulses is this large dead time, which is dictated by the laser's repetition rate. So how often do those pulses in the pulse train come in, which for our laser setup was using 500 hertz. So that's, a femtosecond pulse, then 2 milliseconds of dead time, and then another femtosecond pulse, and then 2 milliseconds of dead time. Typically, you don't expect to see phase segregation in these instances because you just don't really accumulate that many charge carriers. Everything kind of relaxes away during the sort of dead times. So we weren't expecting to see phase segregation, but of course, going back to this picture, visually we were seeing very clear indications of phase segregation, which made us kind of scratch our heads a little bit. And so we sort of wanted to kind of take a step back and say, well, okay, looks like we're phase segregating, but we're doing these experiments on TiO2 because we wanted to look at that electron injection process. So first we had to ask ourselves, okay, what is the significance of this substrate TiO2 in this particular experiment, right? It's an electron acceptor, so we should compare something that's more insulating, something that's not going to have this electron injection phenomenon. And then the other thing that we sort of had to realize was, well, we're also doing these experiments just in ambient conditions, in air, which has oxygen. Oxygen, of course, is a very, very good electron scavenger. So we have to kind of, look at these two different sort of aspects of this process to kind of deconvolute what's happening in this particular experiment. And so again, before we had sort of just this initial and this final phase, we wanted to sort of track the evolution of these excited state features during the course of this sort of 10 minutes of pulse laser excitation. Okay, so we're going to be talking a lot about transient absorption spectroscopy. So I think it's good to kind of take a step back and sort of introduce the concept of transient absorption, since this is sort of, a technique that's a little more sort of out there. But, we can boil it down to, a few simple steps. You can think of transient absorption as step one is just taking an absorption of the sample in the ground state. So we can assume that all the electrons are sitting in the valence band, sitting in the ground state of the system. And in this case, we use a white light pulse to basically just take a simple UV-vis absorption spectrum. And of course, transitions across this band gap for perovskites will give you a feature that looks something like this. So that's step one. Step two is we want to pump the system into the excited state. So for our laser system, a 387 nanometer, 150 femtosecond pulse width laser comes in. we excite a bunch of electrons into the conduction band, and of course, those electrons want to relax back down pretty quickly. So we have to probe the system very, very quickly with another absorbance spectrum. So in the picosecond to nanosecond time scale is when we basically pump and then immediately probe the system while it's still in the excited state. And what that ends up giving is that gives us new absorption features as those excited electrons now start to get pushed around because of this white light probe. So that can start to induce new absorption features in different regions. And oftentimes we get less of this transition happening from ground state to excited state because we already pumped up so many electrons into higher excited states using our pump pulse. So you expect to see sort of decreases in absorption in different areas. But of course, in transient absorption, we basically just take the difference between the ground state and the excited state absorption, and we produce this difference absorption spectrum, which allows us to sort of fingerprint what different species are present in the system. And I will just sort of make a little bit of a special note. In a typical transient absorption spectrum or transient absorption experiment, you would vary the delta T between when you pump and when you probe the system in order to basically watch those electrons relaxing back down to the ground state. But for our experiments, what we wanted to do actually was sort of a modified transient absorption experiment. In this case, we were fixing the delta T between pump and probe at exactly 5 picoseconds, because that gives us time to sort of look at the excited state features, but before everything has a chance to migrate to these iodide-rich domains. Because if you look over the time course, even if you have a very small percentage, phase segregated iodide-rich domains, for example, in photoluminescence, your sample and your signal will be entirely dominated by that iodide-rich domain. In this case, we wanted to sort of look at those initial excited state features that are produced, because that gives us a fingerprint of what's there in terms of the charge carriers before they have a chance to migrate around. So in this case, what we're doing is we're fixing that delta T, and what we're varying over time is just the exposure time to that, that pulsed pump laser. I'll take a little bit of an aside here just to sort of mention, if you're interested in spectroscopy, this time-resolved, transient absorption spectroscopy, over sort of the pandemic, my little pandemic lockdown project was to actually record several YouTube videos explaining sort of from very first principles, what is the principle of transient absorption spectroscopy, what's the instrumentation for this, and also for time-resolved photoluminescence using TC-SPC, there's also a YouTube video out there. So if you're interested, if you're a little spectroscopic curious, and you want to learn more about these techniques, these are really good resources that I'll just sort of plug real quick if you're interested in kind of learning more about these techniques. Okay, so with that, let's look back at the data, right? We have our mixed halide perovskite, methylammonium, lead, bromide, iodide 50-50 on TiO2, our electron transporting layer, and exposed to air, since that was what we initially saw these changes. And the black trace here, this is the initial sort of excited state absorption feature, right, at 0 minutes of laser excitation. And over the time course of about 15 minutes, we see something interesting. We see a decrease in this mixed halide perovskite bleach feature and the concomitant increase in an absorbing feature from the bromide-rich perovskite around 525 nanometers and one down here around 750 nanometers. And this is very well described to almost a pure bromide-rich phase and nearly a pure iodide-rich phase. If you actually overlay and separately synthesize the pure iodide and bromide, it's almost a 1-to-1 overlap. This kind of tells us we're consuming the mixed halide perovskite and generating the halide-enriched domains over the time course of those 15 minutes. But interestingly, if we swap out the actual substrate, now not for TiO2, but for zirconia, leaving everything the same, we see a very different response, actually. Over the course of 15 minutes, we get a little bit of a blue shift and a decrease in these bleach features, likely indicating some degree of maybe photodegradation just due to that constant laser exposure. But we don't see any bromide-rich domains forming here or any iodide-rich domains forming around 750 nanometers. So it looks like in this case, by switching out the substrate, we're basically halting the phase segregation process. And if we think about things in terms of sort of the energy level alignments, right, in the TiO2 case, we can of course inject electrons into TiO2, right? It's a very good electron transporting layer. Versus with zirconia, this gives us, a case where we have a very, very wide band gap insulator. There's going to be no electron or hole movement into the substrate. And so it looks like, okay, there's some sort of effect possibly to the substrate in this case. But we also have to remember the fact that we are doing these experiments in oxygen. And oxygen being such a good electronic scavenger, it makes us sort of ask the next question, which is what is the role exactly of oxygen in these cases, right? Because in both of these systems, we're using just ambient conditions, air is present, oxygen is present. So the next sort of control experiment we wanted to do was take the mixed halide perovskite on TiO2, but now just fully degas the system. right? We basically have it in a cuvette, we pump down, we refill with nitrogen, do that for multiple cycles, and you remove oxygen from the system. So now we can still inject electrons into TiO2, but we don't have that extra effect. And the interesting thing is when we look at the data, we actually recover back something that looks a lot like the zirconia case, right? We get a little bit of a blue shift and a decrease in this transient absorption feature, but no formation of a bromide-rich or an iodide-rich domain. Thus, just by removing oxygen, we actually halt phase segregation under these conditions. And if you kind of compare left and right, these are the exact same substrates, now just sort of different conditions in terms of whether or not you degas the system. So it's clear that it's not just the TiO2 substrate that's sort of affecting things. There's sort of this dual effect of having oxygen as well. That's actually quite important for inducing this segregation phenomenon. So again, there's zirconia case in air, looks a lot similar to the TiO2 case when no oxygen is present, no phase segregation. Only in this sort of unique case where we have the TiO2 plus the oxygen do we see all these sort of markers of typical segregation. And so if we kind of think about things in terms of what's happening with the charge carriers, right, this is a unique case where we're basically extracting selectively the electrons out of the system through TiO2 and into oxygen. And what that's essentially going to do then, we started to hypothesize, well, if we're just pulling out one charge carrier selectively, we're going to have a lot of accumulation of uncompensated holes in the system, right? This is sort of a very extreme case of really unbalanced charge extraction leading to this accumulation of holes. And so we started to say, okay, it looks like these holes are sort of playing this unique role. So the next thing we wanted to see was, okay, if our hypothesis is that the photogenerated holes are responsible for phase segregation, if we think of them as sort of a reactant in the overall process, then we should also see an intensity dependence to this process, right? Since the number of photogenerated holes is going to be proportional to the laser intensity. So this is number of charge carriers is equal to J, the laser intensity or the laser fluence, times alpha, which is the absorption cross-section, which is basically the same throughout the experiment. And indeed, when we do this experiment with multiple different laser intensities, we can see that when we fit these kinetics of these absorbance changes, we see directly the rate versus the carrier density or versus the intensity of the laser directly shows that indeed this is sort of a photo-induced process that requires sort of a higher concentration of holes in order to actually drive this phase segregation. So this implies charge carriers specifically, we're saying kind of holes, or we're hypothesizing that this case is the necessary requirement for segregation. Okay, so far, we see sort of this selective extraction of electrons. We're assuming we're just sort of building up a lot of large hole concentration. So we sort of asked ourselves next, fairly natural question, which is, well, what happens if we just sort of balance the electron and the hole extraction on both sides of the perovskite? Can that actually halt phase segregation? And so in order to do that, what we did was we took basically our TiO2 perovskite film and just deposited near your prototypical hole transport layer spherometad, right? So this is now looking more, not so much like a half cell, but more like what a typical solar cell would look like, where you have electrons and holes being taken care of. And when we take this film and expose it to the exact same laser radiation conditions for 15 minutes, we recover back basically a stable perovskite film, right? No bromide-rich regions, no iodide-rich regions being formed. All we see is a little bit of this decrease in the bleach feature, again, likely due to just a little bit of photo degradation from that laser exposure. But the really interesting thing is, this kind of shows us that, okay, if you balance and take care of the electrons and the holes at similar rates, this can actually prevent the perovskite from phase segregating. So far, what we kind of can conclude so far is that phase segregation is only happening under these particular laser excitation experiments when we have this sort of very, very severe hole accumulation and the selective extraction of electrons. But we can directly suppress that process when we actually take care of the holes as well. And so initially, this made us think, okay, it's really sort of this balance of charge extraction that's a crucial step to maintaining your optoelectronic properties and your actual phase purity of your mixed halide perovskite solar cells. But sort of, we did this initial sort of study, but we wanted to kind of push things a little bit further and kind of look more at this whole accumulation mechanism. So what we've shown before, or just now in the previous slides, is sort of modulating phase segregation through this photo-induced charge extraction. But this, what we've just talked about so far, is kind of a binary case, right? We're either fully extracting the electrons and building up all these holes, or we're fully balancing sort of the hole and the electron extraction. But this is a relatively binary case. What we wanted to do sort of in the follow-up studies was ask ourselves the question, can we sort of fine-tune this process a little bit more? And in that case, what we wanted to do was use electrochemical bias, or essentially electrochemistry in this case, to precisely tune hole and electron extraction. And so in this case, what we wanted to do is basically make a similar system where we have our mixed halide perovskite on TiO2, but now we wire everything to an electrode and we do an electrochemical experiment, right? And the beauty of electrochemistry is you can basically bias the electrode, your working electrode, and you can start to shift around the Fermi level and basically shift around the energy levels of this system. And so now instead of having, something like TiO2 mixed halide perovskite spiro, we have FTO as a transparent electrode, TiO2 in our mixed halide perovskite, and then we'll have an electrolyte solution out there, which allows us to basically do our electrochemical experiment. And so we wanted to ask ourselves basically, depending on the Fermi level position, how do we modulate a charge extraction, and how does that eventually affect that whole accumulation that we were seeing in sort of the previous process? And so before I sort of talk about this electrochemical stuff, what I want to sort of talk about real quick is sort of just a little bit of nomenclature. Phase segregation versus something we call iodide expulsion. So we've talked about so far as phase segregation, right? It's a light-induced process. You form these iodide and these bromide-rich domains. But of course, when we turn the light off, everything basically remixes back to its initial phase because of this entropic driving force. And this is what we typically see, right? Reversible phase segregation, reversible optical and structural changes in the film. Now, in order to do electrochemical experiments, right, we have to be in contact with a liquid solution to have that electrolyte there. And so in liquid solutions, we actually see something that's basically one step past phase segregation, which we term iodide expulsion. So in contact with the solvent, you basically make as an intermediate the segregated phase that has iodide and bromide-rich domains. But in the typical solvent systems that are stable with perovskites like dichloromethane or toluene, what ends up happening is once you form an iodide-rich domain, that iodide actually starts to dissolve into solution selectively. So even though you make sort of this intermediate segregated film, you start to actually selectively dissolve that iodide away into solution, and that starts to enrich the film as a more bromide-rich film. So instead of getting reversible nice changes in the UV-vis absorption, you end up getting basically a blue shift of that absorption feature here, and that's sort of reflecting the loss of iodine continually into the bulk solution. So when we're doing electrochemical experiments, we're sort of taking from phase segregation and just going one step further to iodide expulsion, just because of this requirement essentially for doing things in electrolyte. Okay, so if we want to go back and sort of ask ourselves the questions, can we electrochemically tune the energy levels and modulate this sort of photo-induced process? The first thing that you want to do when doing these sort of electrochemistry experiments is find where your system is actually stable. And so the idea behind the experimental setup here is we're going to have our perovskite as basically the working electrode, right, on FTO and TiO2, our reference electrode, silver-silver chloride pseudo-reference, a counter electrode, platinum mesh, everything in electrolyte. And we're basically going to record the absorbance of the film as we basically bias in different directions, right? And so that's what I'm showing here. This is absorbance as the black traces versus the current response that we see as we basically apply different potentials. And we start from 0 volts versus silver chloride and go in the cathodic direction, more negative. We end up basically seeing, okay, there's sort of this stable window where not much is really happening. And eventually over here, past about negative 0.6 volts versus silver chloride, we see a very large current response and basically a decrease in the absorption of the perovskite. And so that tells us that we start driving some sort of Faraday process out here if we basically go too negative. We basically start directly doing electrochemistry on the perovskite itself. And so that tells us, okay, don't go too far in the cathodic direction, go to about negative 0.3 volts versus silver chloride. When we take another film and do the same thing, but go in the anodic direction, so from 0 volts on sort of more positively, we basically see a similar response. There's a region where things are nice and flat, and then eventually we start to see this large current response, and then this basically degradation, in this case oxidation of the perovskite. And so this allows us to sort of look in this sort of shaded region from about negative 0.3 to 0.5 volts versus silver chloride. This is the region where we can start to tune the Fermi level of the system without directly driving any degradation processes electrochemically. So this establishes what is sort of the stable window for this system. So once we sort of took care of step one, the next step was we wanted to, of course, induce this iodide expulsion, right, this phase segregation process with these different applied biases. So again, we're going to do a fairly similar experiment, working electrode as the perovskite, recording absorbance, applying potential, but now we also have to bring in a 405 nanometer laser to basically excite and generate those photo-induced charge carriers. So just sort of to give an idea of what this looks like, actually the experimental setup, this is sort of an early experimental setup where we have our 405 nanometer laser shining onto the system, right? Eventually we moved to a more collimated laser, which made things a bit more reproducible. But the basic idea is you kind of sit your electrochemical cell Your perovskite film is basically being hung in the electrolyte solution, sort of here, right directly in the light path of just very typical kind of UV spectrometer. Off, to the side, we have sort of our potentiostat, which is allowing us to apply these different electrochemical potentials. But essentially, this is sort of like a spectral electrochemical measurement, which in terms of, difficulty in terms of setup, it's actually fairly straightforward if you have a potentiostat, a UV vis, a laser, and then, some slightly custom glassware. But this is sort of just, visually what this kind of experiment looks like. Okay, so now we're going to be shining light, applying bias. What does the actual data look like? So looking now at the steady state absorbance features at 0 volts versus silver chloride, essentially what we see is over the time course of 60 minutes of irradiation, we see again this blue shift in the absorption feature, right? That's because we're continually dissolving iodide as we're phase segregating. And that gives us basically these new absorption features from the bromide-rich perovskite and maybe a little bit left over from the mixed halide. When we go in the anodic direction, now we're applying 0.5 volts versus silver chloride while continually irradiating. We see basically a very qualitatively similar response, but now the time scale is only 15 minutes, right? So we get almost the same degree of segregation and iodide expulsion, but in a much, much shorter time. And similarly, if we go in sort of the cathodic direction, what we see is at negative 0.3 volts versus silver chloride, over the time course of 60 minutes, we only get maybe, like a 20 nanometer blue shift, but not nearly the same degree of change that we were seeing at these other potentials. So directly, we're seeing this influence of applied potential on this photo-induced process. And so, of course, this is the steady state absorbance or the typical absorbance spectra. If we look at the difference absorption, so just subtracting this initial absorbance feature from all subsequent traces, this sort of better highlights the fact that you get a decrease in absorption over time around 625 nanometers as you lose that mixed halide phase. And you can even see little humps here in the difference absorbance spectrum from that bromide-rich phase kind of growing in over time. Again, this isn't transient absorption, this is just a differential absorption from the steady state absorbance over the different time series. And so what we do is we basically take the absorbance traces over time and we back out the kinetics of this process, right? So this is the change in absorption versus time at that bleach feature around 625 nanometers for multiple different applied potentials in this process. And when we fit the kinetics of this with a simple sort of pseudo-exponential or pseudo-first order process, what we get is the rate constant of iodide expulsion demonstrates a very clear response based on the applied potential, right? It's fastest in the case that we're applying 0.5 volts versus silver chloride, and we get a direct suppression of that once we go to more negative potentials. And not only does the rate change, but if we actually look at the films morphologically through SEM, in the case where we apply the 0.5 volts versus silver chloride, we get the most degree of phase segregation, we get the most dissolution and basically chewing up of the perovskite film. Whereas if we apply 0 volts versus silver chloride, right, you still see some pinholes, right? There is still that phase segregation process happening and the iodide expulsion, but not nearly to the same degree. And of course, in the case of negative 0.3 volts versus silver chloride, where we suppress to a very large degree phase segregation, we basically maintain the morphology of the system. Okay, so what's exactly happening when we're doing this sort of biasing plus shining light? Well, in the case where we're really driving this fairly fast under anodic conditions, we can imagine from sort of an energy level diagram, right? We're exciting the halide perovskite, right? We're pushing electrons, into the conduction band. We know that's going to inject into TiO2 pretty readily. And from here, the electrons can either back recombine with the hole in the mixed halide perovskite, or if we're anodically biasing things and pushing the Fermi level down, that gives us a very strong driving force for electron transfer and extraction into basically the electrode, right? So we expect in this case to have a very severe degree of basically charge separation, right? Pulling out these electrons from the system and leaving a large degree of hole accumulation. And indeed, that gives us the largest degree of phase segregation. Whereas under the cathodic bias conditions, if we push the Fermi level up, right, from the perspective of the electrons, there's now a much smaller driving force for actual removal of those electrons from the system, right? So we expect the electrons to basically start back recombining with the hole in the perovskite, and that should basically suppress hole accumulation, right? We're still generating electrons and holes at the same time, but what we're modulating in this case over this potential range is essentially to what degree is there a driving force for fully extracting them or allowing things to basically recombine. And then indeed, if we also look at the intensity dependence, in these cases where we're biasing more cathodically, where we suppress the process, we require a lot larger laser intensity in order to drive this process, whereas under these conditions where we're having a stronger driving force, the laser intensity required to drive this process is a lot lower. So these sort of things sort of directly kind of correlate with each other. So from this electrochemical set of experiments, we can basically say, this iodide expulsion is basically the corollary to phase segregation. We can see directly by modulating that Fermi level, we can actually induce more accumulation under basically conditions of very strong electron driving force for extraction, or we can basically induce a lot less whole accumulation by lowering that driving force for charge extraction. And so it really tells us is that the internal Fermi level, right, that's actually operating under these devices in like a perovskite solar cell, this is directly impacting those thermodynamic driving forces for electron extraction, and that importantly modulates what's happening with the holes in the system. And so I think, though, if you want to sort of give like a two-sentence summary over the course of what the Kamat lab has been able to look at, if we kind of think about what's happening with these holes, right? The two-sentence summary is basically holes, whether they're generated photochemically, which is what we've talked about today, right? Shining light, producing charged carriers, and either modulating that extraction with electrochemistry. That's all photochemical processes. In the past, we've also looked at purely electrochemical hole injection. And we see basically the same thing. You induce this phase segregation process when you have basically introduction of holes that are uncompensated in the system. But the sort of summary of those holes, these have a very strong thermodynamic driving force for trapping at the iodide sites. Right, the holes are going to move to basically what's the easiestly oxidizable halide ion in the system. That's going to be iodide in these cases. And basically, you trap the holes very quickly because of the strong thermodynamic driving force, right? At these iodide sites, this induces basically a free iodide that's able to hop through the lattice. There's been other groups that have kind of shown the fact that you can sort of get these iodide atoms moving through these interstitial sites in the actual perovskite. But really, sort of the initial process that sets everything off is this initial hole trapping and oxidizing of basically those iodide atoms, and that mobilizes the iodine basically to move through the lattice and drive phase segregation. And so recently we've sort of summarized a lot of this sort of the last 7 or so years of work in this recent sort of accounts paper if you're interested in sort of reading more. But sort of, I think, the basic sort of picture that we have is thermodynamically, there's unfortunately a very strong driving force for this halide oxidation. But I think really where the field is starting to move to, and has been moving to for a while, is this idea of, thermodynamically, we're kind of hosed when it comes to phase segregation, right? Thermodynamically, there's a very strong driving force, which is why a lot of folks are looking sort of more kinetically at sort of slowing down and trapping these processes. And a lot of that has to do with interfacial engineering, right? You can put basically a thin layer of the 2D perovskite, which can basically halt the movement of those mobile iodide atoms. There's folks that have also looked at putting graphene layers at these interfaces, right? Because a lot of us know and have been exposed to this idea that the iodide can actually move through the perovskite, it can move through the whole transport layer and even start reacting with gold contacts. So if you can start to basically impede some of that progress of these mobile iodine atoms, the realm of thermodynamics is kind of, it is what it is, but the realm of kinetics and slowing down and kind of trapping these processes seems to be where a lot of sort of the field kind of needs to move to in order to make these devices more stable. So with that, I know I've gone a little bit over the kind of typical 30-minute time slot. So I'll go ahead and sort of wrap things up with a conclusion and thank these folks in the Kamat lab over the years that have helped me in my PhD, these PhD funding sources. If you're interested in the paper details, it's shown here in addition to that accounts article. And then I'll go ahead and also give a little bit of a shout out to my current postdoc lab, since I am on their watch giving this talk. And again, thank you all for letting me kind of drone on and talk a little bit about my PhD work. And of course, I'd be very happy to take any questions or any comments on the talk.